Introduce our presenters for today's webinar. We have with us Kenneth Ozuna and Sarah DeMoya. Kenneth Ozuna is the Area Bridge Section Manager for HDR. Mr. Ozuna comes with an extensive background in managing multiple teams in bridge layout, bridge design, and structural detailing. He has extensive knowledge in rehabilitation, restoration, and repairs of bridges. He's also knowledgeable in bridge construction techniques, repair techniques, and construction resolution. He is the project manager for the south approach of the Houston Ship Channel Bridge Replacement Project. Miss Sarah DeMoya is a structural engineer for HDAR. Miss DeMoya received her BS in Civil Engineering and Construction Management from Rice University and her MS in Structural Engineering from the University of Texas at Austin. In her 10 years in bridge design, she has worked on alternative and traditional delivery projects, signature bridges, bridge rehabilitations, bridge widenings, and military vehicle bridges. Most recently, Ms. DeMoya served as the Deputy Project Manager for HDR's design of twin approach bridges on the Houston Ship Channel Corridor. She was responsible for internal and external coordination between project teams throughout the 18-month design process. Okay, Kenneth and Sarah, it is all yours.
All right, thank you. Hi, like I said, my name is Kenny Ozuna, the project manager for the South Main Bridge approach to the Beltway 8, owned by Hector Toll Road Authority over Houston Ship Channel. And the current slide shows a picture of the existing bridge. The one feature to note here is that the columns are in the water. As you can see, a ship is traversing underneath it and is able to impact the columns today. So that's part of the safety features that the new bridge will replace. Like I said, my name is Kenny Ozuna, and my colleagues joining me today is Sarah DeMoya. The presentation is going to be broken down into two components. I'm going to take the first component that's going to talk about the site constraints, some of the hardships, the ins and outs working in a difficult site in an industrial application. Also, where the facility is alive, we're building a bridge within a live facility, and some of the ins and outs of how we're going to provide construction access and accommodate the pipelines and railroads and stuff like that. And Sarah's going to take the second half and talk about the technical aspects of the design, why some key decisions were made, and moving forward. It's copyright materials. Let us know what you need if you need it. So just a brief overview. This is a shot of Houston, Texas, and the project is located on the east side of town. North is to the top. Houston Ship Channel. Houston has 3 loops. The first smaller one is Loop 610. The second one, where our project is located, is Beltway 8, a toll road loop. And then there's loosely an outer loop on the left side that's called State Highway 99 or the Grand Parkway. A closer up view shows the project site. Bisecting right to the middle of the red circle site is the Houston Ship Channel, also known as Buffalo Bayou. So as you can see, one key point of this slide is you can see that the port side development is a very busy port, ships going in and out daily basis, trains, pipelines, all serving our petrochem needs throughout the nation. Here's an overview of the project in a schematic sense. From left to right is upstation. Also, left to right is the same as north. So starting on the left is the south approach at the 225 interchange, and that's leading up to the South Main Bridge approach, which is called segment 2. It's the first portion on the left in orange. That was designed by us, HDR. Segment 3 is the actual main bridge or the channel spans. Segment 4 is the equal and opposite North Main Bridge approach. And segment 5 is the final tail end of the project, or it's the North Approach segment. So let's talk about how the bridge project was broken out into independent design teams. For a project of this magnitude, it required that we have a GEC, General Engineering Consultant. That was also done by Dannenbaum, but Dannenbaum was also a segment 1 designer. So in sequence of the last slide, you have Dannenbaum on segment 1, HDR did the South Main Bridge approach, segment 2, which consisted of TxGirder superstructure. It was approximately 5,400 linear foot of twin structure that came out to about 780,000 square foot of bridge deck with an approximate construction cost of $95 million. And that's just the south approach of the bridge. So going over the bridge, traversing the channel, you have FIG designing the main channel span, also known as segment 3 of the contract. Okay, it's a cable stayed segmental. It's about 2720 linear foot, but it's twin signature bridge structure, equaling about 383,000 square foot of bridge deck. And their approximate bridge cost was upwards of $415 million. And that's only the portion for the main channel span. On the departure end, HNTB designed the North Main Bridge approach, or segment 4. It's also comprised of TxGirders, and its length is about 2,900 linear foot, the same twin structure, equaling about 408,000 square foot of bridge deck. And the North Main Bridge approach approximate construction cost at $47 million. So you have this bridge that's adding up to South Main Bridge approach at $95 million, plus the main channel span at $415 million, plus the $47 million of the North Bridge main approach, and boom, you have almost a $600 million structure, with tack-ons at the end being Dannenbaum at the south end and LJA Costello on the north end with a couple of accessory bridges. So some of the breakdowns of teams to manage the design of a project of this magnitude. Dannenbaum, who is also a segment designer, was the project management consultant. They oversaw and helped the owner entity facilitate all the meetings and the coordination of the workshops required to make sure that all discipline teams were on the same page and designing the same stuff. Corridor-wide, we had Fugro, Geotest, and Paradigm geotechnical engineers to help pull it all together. It was quite a demanding geotechnical investigation, or as you can imagine, for such a large bridge, large loads, tall towers. Additionally, we had McDonough, who was a corridor utility consultant. Later, you're going to see the magnitude of pipelines and crossings within our right-of-way, and it certainly benefit from having a singular engineer who was able to coordinate and facilitate with all the pipeline owners to get the project successfully pushed through. Also, you had PB and Dannenbaum acting as the corridor drainage consultants. The project is located in the 100-year flood zone. For survey control, we had Landtech, Dannenbaum, and Weiser. Corridor-wide, they got it together and made sure that we were all on the same page in X and Y and Z fashion. HNTB also, while they were also a designer for the North Bridge main approach, they were also acted as the corridor environmental, handling the permitting, the Coast Guard, wetlands, and the CTMS, the electronic tolling functionality that the owner entity required for this project. This is the limits of the project are within electronic only toll collection. No more manual collection is the goal in Houston. Tech Engineers is they acted as the corridor signing and pavement marking consultant. Big Engineers, who also did the main channel design, acted as the corridor aesthetics consultant. So getting down a little closer to the bridge, there's a little cross-section showing that we have a northbound and southbound twin structures, parallel structure with an air gap of approximately 21 foot 2 inches. They're connected only at the pylons at the ship channel main span, and the overall bridge width each direction is about 71 foot, and that makes up with 4 12-foot lanes and 2 10-foot shoulders in each direction. A significant improvement over the existing structure, which is shoehorned in 4 lanes of traffic with no shoulders to speak of. So how did we do some of the internal and design team communication? Well, typically we have monthly main bridge meetings, including all consultants in the same room. The meeting was conducted by the PMC and the owner, Hectra, and each consultant owner was in attendance and gave a progress update. And at the end, we were able to identify action items from each individual other engineering firm, and also to cross-communicate what we were doing and what might be a good idea for others to consider. Additionally, we had monthly one-on-one meetings with the PMC and the owner, Hectra, and those were private meetings where we reviewed individual consultants' progress, issues, concerns. Also, we had quarterly workshop meetings. Specifically, they were geared towards geotechnical workshops, getting all the designers in the same room with the geotech to resolve some of the nuances of the soils below. Also to hash out some workshops to hash out and discuss some of the aesthetics and how they were going to impact the analysis and the detailing of certain aspects like the columns and the bent caps and the retaining walls. And also for a project of this magnitude, we had to get our minds together and determine how we were going to construction package this project. To allocate over $900 million total in a corridor-wide manner, you want to progressively release that money in a phased fashion so you don't basically tie up your $900 million all up front while it's just sitting there. Also, you don't want to have a project that's completed in advance and not being used to avoid that negative public perception. So everything was in concert, detailed so that it was sequenced with each other, so that the end dates would coincide with opening of traffic. Also, let's not forget the obvious. Regular phone calls and emails and personal conversations are really the best way to facilitate progress of a design. So let's talk a little bit about construction sequence. The existing bridge is shown on your right, and it's currently configured to handle two-way traffic, northbound and southbound, or into the screen and out of the screen. So what we'll be doing is we're going to build the bridge shown in the cross-section on the left side. That is actually the southbound bridge alignment. Remember, there's twin structures. You can have a left side and a right side bridge. Only in this view, the right side is occupied by the existing structure, which is in use during our construction of the left side section. So we're going to build this left side section, which is known as the southbound bridge, and we're going to configure it with two-way traffic. Okay. Then we're going to switch the traffic to the new structure. Then we're going to demolish the existing bridge, and then we're going to, after we switch the traffic, we can begin demolishing of the existing structure, and that frees up that land to begin construction of the northbound new ship channel bridge. Like I said, the final configuration for each direction will be 4 lanes with 10-foot shoulders on each side, each direction. The main channel span, that's what basically looks like a 3-span unit centered on the Houston Ship Channel. The design is by FIG engineers. It's a segmental cable stay design. The main span is 1,320 foot with 2 460-foot back spans plus 2 more 240-foot side spans for an overall total length of 2,720 linear foot. If you look in the artist rendering, the key point there is that the towers and their foundations are right at the water side. They're not available for ship impact, as a ship would ground before it could connect with the main pylons. So that is a safety feature of the new structure. Vertical clearance is going to stay the same at 175 foot, the same as before. FIG worked with Hector, the owner, on visual quality and aesthetics in determining the rail type, number of columns per bent, the column and the bend shape, bridge lighting, wall surface finish, to name a few. They did this for the entire program so that we would have a consistent corridor aesthetic package of details. So about the Houston Ship Channel, this is the same picture of the old bridge with the ship underneath it. Currently, it's a 500-foot wide navigation channel with 175-foot vertical clearance. There is future plans to widen the channel out to 530 foot. Additionally, they want to go 5 foot deeper on the channel expansion. Hasn't happened yet, but we are prepared in the new bridge cross-section to handle it. So we're going to dive on down closer into the weeds here and talk about the South Main Bridge elevation, the design that we did in-house over here at HDR. And it's about a little over a mile long of twin structure. And like I said, from left to right is heading north and is also up station. And orange is the portion of bridge that we designed personally. And the red portion is the main channel spans designed by FIG. But what you see here is over on the left is you can see where we have future tie-in ramps in aqua blue. And the bridge curves around and it goes over some significant amount of roadway and a railroad right-of-way. We're going to show this in a couple slides later. But more importantly, what you see here is where the text that's depicting Sam Houston Tollway East, that text is the portion of the bridge is within the confines of an active and ongoing Kinder Morgan facility. The bridge is in there by easement. It's not right of way, so we have to work in cooperation with the owner of that facility, and it makes for some, it makes for some difficulties in construction site access, where you're going to park all the employees, or you're going to bus them in, bus them out. Just some human considerations to consider to install a bridge in somebody else's facility. So let's dive down and talk about some of the key features of the South Main Bridge approach. It's 42 spans, each direction, southbound and northbound. As I mentioned, they are separate structures. The overall length for each side is about 5,387 linear foot. The overall width is 70 foot 11 inches. The existing vertical curve of the old bridge is very steep, and it's shown in the black line here. It's a very steep bridge. If you've ever driven on it, it's steep and narrow, uncomfortably so. It's at 5%, so it starts to climb later by station than the proposed structure shown in orange on the cross section. We have a much gentler, more user-friendly grade at about 3% climb, and of course, a climb of 3% begins earlier than the existing 5% steep grade. So Like I mentioned, on the left side of the plan view in teal, we show that we have stub outs to accommodate the future State Highway 225 direct connectors at the south end or the left end. Navigable channel clearance that we're heading towards using tall column construction is about 175 foot off the water for navigation clearance. Again, the South Main Bridge approach, you can see in the on the graphic on the right side, twin structures, each direction, southbound, northbound, 71 foot wide almost, designed by HDR. And the superstructure is comprised of prestressed concrete TxGirders, TX70 to 70-inch deep prestressed concrete beam. We have them at about nominally about 150 foot spans on average. Of course, at the south end where we're prepared, where we're stubbed out, widened out to receive and accommodate the direct connectors, the slab is tapered out. So we have a tapering deck at the beginnings or south end of the bridge. Some of the other constraints was we needed to avoid and traverse over UPRR and PTRA railroad tracks. We had a road, an in and out road that serves the port users called Jones Channel City Road. And also we had the bridge traverses over 70 plus utilities. And also, if that weren't enough, going through down the center line of the bridge on a flat skew, I'll show it in plan view in a minute, we have a 10 by 20 foot skewed box culvert that the story goes it drains Pasadena. But another part of the story is that nobody claims ownership to it, so meaning they don't want to maintain it. So also, as I mentioned, the bridge is going to be constructed within Kinder Morgan's processing facilities, an active port facility. And also we have to miss existing bridge foundations for today's bridge. So again, on the left side is the south side, headed left to right is north, and we're starting at the beginning of our ship channel, our South Main Bridge approach. And the side here just featuring the flared out portion of the bridge that to receive the direct connectors for future interchange at 225. Also, you can see Jones Channel City Road in yellow. That is an in and out access road for all the port users. If you talk to different people, upwards of 1,500 workers, all exiting at the same shift change. So there's some traffic down there, and also that's the main in and out road for access to this South Main Bridge approach for our contractor to deliver all the materials and get his men and personnel inside the gate of Kinder Morgan. Also, you can see that we had temporary construction easements. We had to demarcate what the needs were for heavy lifting, the crane needs to lift the beam and put it in place. And we have a parallel temporary construction easement identified throughout the set of plans that we have access to. And of course, then we're heading towards the proposed railroad tracks and some other pipeline easements. So we're going to talk about some of the site constraints as we move from left to right or north or up station, as I mentioned. And again, we have Jones Channel City Road in yellow. And the first easement that we're crossing over is the UPRR. It's an 80-foot easement. I got twin tracks in there. Had to basically make the clearance windows for all the while we have live train traffic underneath. Adjacent to the UPRR easement is what's known as Pipeline Alley, and that's the official name within the easement. And it's quite a wide, dedicated easement that houses many pipelines of caustic nature and volatile compounds within the pipelines. And this is the Houston Ship Channel feeding all the industry to make plastics, oil, gas, you name it. Moving north, adjacent to the other side of Pipeline Alley is 100 foot of PTRA, that's Port Terminal Rail Association easement. They have a single track in there. So as you can see, the red band is a hot zone of touchdown points for our bridge foundations as to whose property are we going to be on, whose pipelines are we going to land on, and we need to be very careful with where we're going to put our foundations. Again, you can see Jones Channel City Road in yellow. That's underneath the bridge, creating the need for straddle bends so that the road can pass underneath the bridge. And now you're seeing some blue lines that delineate the property limits of Kinder Morgan. Okay. Also, you can see on the right side of the graphic, you can see 3 private Kinder Morgan tracks that are your first impediment if they have trains and blocking Jones Channel City Road. What to do? Well, we'll talk about that. There's a little go around for construction access. So here we are with the existing bridge, and we're showing some of the easements that were just highlighted in red. And this is the same thing where you have 80-foot UPRR easement, then you have the Pipeline Alley coupled with 140-foot with HL&P also has fee strip in there, and 100-foot of PTRA rail right-of-way as well. So when you overlay the proposed bridge on there, well, where are we going to put our foundations? Well, it's kind of simple. The old bridge that's there today has some existing foundations that were successfully installed to avoid the existing obstructions or obstacles at the time. So our plan was to build equally aligned new bridge foundations where we could, knowing that any new pipelines that were installed after the old bridge went in, that they absolutely had to go around the old foundations. Therefore, we kind of knew that that was a clear band, and that's what we researched and looked into. So here we go. This is the highlight of the pipelines that were within Pipeline Alley, and as I mentioned, you can see there are some clear bands of holiday between the pipes that basically are there because the old bridge foundations are there. So we were able to capture that real estate successfully and reinstall our new supports so as to reduce or minimize the amount of relocations of pipelines that we did. There was one pipeline that we did have to relocate, and that happens to be it's a shell water line, and we had to avoid a foundation conflict. And the key takeaway on that one is that it's a water line. All those pipelines are ethylenes and butyl and chlorines under pressure. So it made sense to go for the water line to relocate, since basically it's the safest, and every highway contractor has the ability to relocate it, and it just made the most sense out of the profile of utilities. Additionally, in blue, we have a bunch of overhead electrical transmission lines. In raising the new geometry of the bridge, the raise caused us to violate the clear zones of the existing high power overhead lines above. So the project did require that we relocate, really just raise the existing power lines to meet code for our new geometric grades. Also, what you're seeing here is a snapshot in red now of power lines, and some of the power lines that had to be raised are paralleling Pipeline Alley. Also, the fence line in blue of Kinder Morgan facility, Jones Channel City Road in yellow. Of course, you can see the bridge overlaid over all these obstacles. Pipelines everywhere. So what the pipelines everywhere statement means is that we had to, we couldn't incorporate typical details. Every bridge support turned into a unique and individual footprint of foundation so as to avoid the constraints or obstacles below. So an overview, now we're moving into the confines of Kinder Morgan facility. As I mentioned, the blue line establishes the property line of the facility. And this is where they offload coal from the ship and they put it onto trains and ship it out. So as I mentioned, once you, on the left side, once you enter the facility by Jones Channel City Road in yellow, and you go through a security gate, and then you come across 3 Kinder Morgan tracks, and oftentimes you'll have trains blocking that. So the go around is the yellow go around that parallels the fence, and you can go around and you can the long way and then come back station up towards the 3 tracks that block you. Only if those tracks over there on the right or north side also aren't blocking you. Okay, so Kinder Morgan has cooperated extensively throughout the whole process with us, and it's just going to be a daily communication cycle between Kinder Morgan and the contractor to determine what work needs to be done, what access needs to be done and when, and how to get inside the loop if the loop is entirely blocked. Also, what you see in red in the middle of the screen is an existing conveyor structure, and that is underneath the existing bridge today, and it's how they travel coal through a conveyor belt system to a train loading facility that is out of the scope of this talk. And we had to protect that not only from debris but from construction activities as well. Also, the key feature is that existing box culvert. It's shown in pink and a diagonal, a very flat skew to the bridge alignment. And as I mentioned, it's like twin 10-foot boxes draining all of Pasadena, yet nobody claims ownership to it. Nobody knows who installed it or paid for it. Early on in the design of the project, we looked at relocating that box and pulling it out and providing for drainage somewhere else. But in the end, we decided to let that sleeping dog lie, not to touch it so as we would not be blamed for future flooding. Very important in the Houston area. Again, going back, what further means that with such a flat skew of this diagonal box shown in pink, many of those bends are not typical, and they're one-offs and were just resulted in specific design, or i.e. column spacing and foundation spacing and clearances to accommodate and to avoid damages to the box. Okay, so I'm going to hand it off to Ms. Sarah DeMoya for a presentation on some of the technical aspects of our project.
Thanks, Kenny. So regardless of all the site conditions that are difficult in this project, we went through a rigorous design progress. We were asked by our client, Hectra, to try to make the details as consistent as possible between the different design consultants. So you can imagine, you know, working within your own team, it's hard to keep 2 structural engineers on the same path, let alone multiple design consultants. So it was really important that we had firm direction on what we were moving forward with. So the first thing we knew when we started the project was that we were going to use TxGirders as our superstructure. At the beginning of negotiations, there was discussion of using segmental on the approach spans, but due to cost and maintenance and unknown construction requirements, the client decided to go with a standard TxGirder design for the approaches. And so that was something we knew at NTP. Once we got into the layout phase, juggling all of the foundations and all that, we needed direction on how many columns we were going to have for our design. So we did a workshop, and Hector ultimately decided to go with 2 column bends throughout the approaches. HDR got a little bit of leeway on that because we had some interesting foundation locations to deal with. So we do have some single column and straddle vents, but in general, the aesthetic is to go with a 2-column vent configuration. Then we moved on to foundation, and a decision was made to go with drill shafts based on Fugro, our geotech consultant's experience in the area, as well as some discussions with contractors on what makes sense for the site conditions. We had a lot of pipelines to deal with. So driven tiling was really not a good option with those constraints. And the other important thing was we went with exposed foundations. Now, what I mean by that is we don't have the foundations buried underneath the ground line as you would typically expect. The reason they did that was because it eliminated temporary special shoring, which is a huge cost for the contractor. And so that was our direction moving forward. We had some other decisions, of which the most important was the aesthetics of the vent caps and the columns, and that really drove our rebar detailing and geometry of all these structural elements. So let's talk about foundation. We went with mono shafts as tall as we could because they were easier to install. They made more sense from the perspective of staying away from utilities and just a smaller footprint to land. So that was, we went up to a 50-foot column height with those until we had to go to footings. And by that time, we were out of the majority of Pipeline Alley and all those railroad tracks. So that really made sense. When we did the monoshaft design, we were closely working with Fugro to design this stuff. They went with a 3.0 safety factor for redundancy on these shafts in Pipeline Alley. We also made sure that if we were within 1 shaft diameter of a buried utility, we went with permanent casing to about 1 shaft diameter below that utility in profile elevation. So that did reduce our capacity slightly, although we had such terrible soil in this location that it wasn't really that big of a deal. We ended up with 8-foot and 10-foot diameter monoshafts. Just for consistency, we didn't want too many sizes. We ended up with a length between 73 and 133 foot. And one important thing that Fugro really wanted us to include in our specifications was quality control of these shafts. They're so important, they're non-redundant. So we have sonic caliper testing as well as thermal integrity profiling included. When they're out there doing CE&I, they can check these shafts to make sure they're installed properly. Some of the detailing, we did have to do non-contact splices because we have a smaller column section going into an oversized drill shaft section. So that's special detailing according to ASCE ORFD. And we did make sure that we included a bundled bar splice so that the contractor knew exactly what we were looking for in the field. One other thing is we did do soil structure interaction modeling on these just because of the height of the columns and the soft soils. We wanted to make sure that our deflections were reasonable. So we used SBMP to look at that. We did find that our deflections were reasonable, less than an inch, and our point of 60 was typically 20 to 30 feet below the top of the shaft. So that's about on par with what TxDOT recommends, a 3D below the ground. With the footings, once we got up higher with the columns, we had to go with footings, and we did go exposed footings. We did model those in FBMP as well to optimize drill shaft lengths and verify we had no shaft in tension. And that was, we were trying to go for typical footings to try to minimize the changes the contractor would have to make. So we went with 4-foot and 6-foot diameter drill shafts on those footings. We were up to about 120-foot drill shaft length. Fugro did do a load test program during the design process to confirm that what they expected the soil to do was actually what it was doing, and they were right on. They were really close. So we really optimized the shaft length. One thing that did happen during the course of the design was we were looking at we were originally starting with 3-foot diameter shafts on our footing, and we got to a point where we were exceeding an L over D of about 30, which is what the FHWA put out a study in 2010 regarding drill shaft construction procedures, and TxGirder went through and looked at it and established some criteria of L over D less than 33 due to constructability and soft soil concerns. So we did go bump up to a 4-foot diameter shaft. That caused us to redesign some stuff because we had to increase the size of our footings, and we were already juggling all those obstacles that Kenny talked about. Columns were unique on this project. They have specific aesthetic requirements. And so you can see that we went from a constant column base section, and then as we move up the column, we're tapering our corner reveals into the section of the column. So with this kind of geometry, it made for interesting detailing. We also wanted to be mindful of repetitive form work to try to minimize the impact of this on the construction cost. So we went with a stepped cartridge type design. Depending on the height of the column, you got a certain tapered length, and then we tacked the base onto the bottom to try to keep the detailing as consistent as possible. We did have a lot of workshops with HNTB because our columns needed to look the same and be detailed the same, so we didn't have mistakes being made because we were detailed differently. Interesting thing about the bent cap is that the column frames into the bent cap. It integrates with the face of the cap. So you can see in section AA, we've got a rectangular cap section, but that's only at the widest point of the column in the alignment direction of the bridge. So as you move over, you can see that our cap is really a tapered section underneath, and that's because it's going down. At the bottom of the cap, it frames into that smaller section of the column along the length of the bent cap. So that created some interesting detailing. We had to make sure all our bars could fit in between our bottom cap reinforcements, and weaving that needle was interesting. So that also required significant coordination with HNTB. We did do some workshops with them. We ultimately ended up, one firm created their details, and we went through and reviewed them, and then we all agreed on something. HDR did have some unique geometry, including some skewed vents, single column vents, and some straddle caps with columns at the end of the cap. So we have some one-offs that are more unique than the standard 2-column vent because of where the footings had to land. And what you don't see on this view is that we did add some end pedestals at the end of each cap, and that was to attach light poles, overhead sign bridges, and also to generally hide the ends of the beams up there. Going on to the superstructure, we have TxGirders. We pushed them to 153-foot span limit. We went with an 8-inch deck, 3-foot overhang. Prestressed concrete deck panels were not allowed by the client based on their previous experience, so everything's going to be PMDF. We did have slotted rail, CTMS, and conduits attached to the deck. And we did have a couple of spans over Pipeline Alley and the railroad where we removed the bottom strands and made the first row of strands a little bit higher in the bottom of that beam to increase the clear cover. That's for extended life during an extreme event. Finally, the transition vent was very interesting, point of coordination with us and FIG at the main channel. The PMC set up an interface program so that all the XYZs were sure to be met. So everybody got buy-off on geometry. And then FIG had a very large finger joint. They had movements on the order of 13 inches at that location because they have such long spans. So the finger joint took care of that. But what affected HDR's design on the approach side was operation of those pylons was creating some movement on the transition vents. And so we had to make sure that when that transition vent moved, that our superstructure was going to be okay. So we had to do special bearing details. We had diaphragms at the end of the girders, and we had some shear blocks in there to make sure the superstructure moved together wherever it did move. Finally, some quantities. We went over this stuff. A lot of concrete, a lot of beams, a lot of deck. Southbound and northbound is basically the same. Northbound is a little bit bigger because it had the direct connector framing in a little bit longer, so it's a wider bridge at the south end. Construction packaging was a big deal on this project. It ended up being broken into 3 construction contracts, and it's scheduled for construction to be complete by 2023. The estimated total project cost was about $960 million, including CE&I, construction, and associated other activities. So the biggest contract was that 345 contract, the first contract to be posted in February of 2017. And that included both the northbound and the southbound portion of the main bridge, as well as the approaches for the southbound bridge. So had lots of meetings. Bids were due in June of this year. The engineer estimated $612 million for that package, and the winning bid came in just under $570 million. We are expecting the Commissioner's Court actually to award that contract today. So it hasn't been awarded as far as I know, but it's probably going to be to Ship Channel Constructors, which is the joint venture between Trailer Brothers and Zachary. And the NTP is expected first quarter of 2018. The contract 346 was the ends, segments 1 and 5, as Kenny discussed, which is the 225 and the approaches leading up to I-10. That was posted for bid in May, and it was awarded to Zachary. I don't have the final bid on that, but it was estimated about $80 million, and they started at the end of last year constructing that one. The last contract is going to be the northbound bridge approach spans, because the main channel span is all in that first big contract. So just the approach spans on the northbound, including demo of the existing bridge. And that's expected to be posted for bid in 2020 with an estimate of $150 million. So I don't know if we have time for questions, but that's what we got.
I think we do have a little bit of time here for questions. Let's see. Got one. You said that the drill shafts were chosen over driven piles, even though the drill shafts are 70 to 100 plus feet in depth.
Yeah. Well, when you get into Pipeline Alley, you realize that those pipes are over 40 years old. We just didn't want to be blamed for the dynamic or the vibration effects that driving piling might have caused there. So that portion of the structure absolutely had to be drill shafts to avoid damages. And then the way the project progressed was we kept on running into very like and similar obstacles that instead of going with alternate foundation details, mixing and matching, people just wound up settling on using drill shafts as the single and main only foundation element.
All right. And on the monoshaft, was that also a pure cap or drill shaft cap with the monoshaft off of it, or is the monoshaft and foundation one system?
Yeah, what that means is it's a single shaft to column connection. So the reason that's advantageous is because it precludes the need for the contractor to excavate and form up and tie the steel and wait for the concrete to cure of a footing proper. So it's while the shaft is rather large, upwards of 10 foot in diameter at times, especially for the taller column heights, it just saves a large amount of time, and time is money.
Time is always money. Okay. Let's see, I don't have any other questions coming in that I can see right now. Give everybody a second to type anything else in here. All right, well, speaking of time is money, Sarah and Kenneth, thank you very much for the presentation. And for everyone who has attended and listened, thank you again for participating in today's ASCE Texas section webinar. As mentioned before, individual registrants should receive an attendance acknowledgement without further action. For those attending with a group, the site coordinator will receive the PDH certificate for distribution. I invite you to visit the Texas section website, texasce.org, to register for the webinars, to learn more about the association, and to take advantage of the benefits of membership. I'm always available for your questions and hope to hear from you soon. Thank you for your attendance and have a great day. 2 announcements.